start the stream.
OS.
Yeah. Of course, I have to fire that up. Thanks for helping with the setup. I really appreciate it. That would be awesome.
I don't know what we can do about the cable, but we'll ask the video guys if they have something. Maybe they have an amplified cable or something.
Yeah, that would work. Or even something with some noise cancellation. This is the slowest panel.
Just a minute or two. Okay, Olivia, have fun.
Thank you.
See you next time.
Yep. Still waiting for... There we go. Pardon?
More stuff.
Yeah. All right.
All right. We're getting a little better here. So next class, I cannot have anybody sitting on the floor in any way, shape, or form, okay? The university has come to their attention how many people are showing up in this room, and that is a fire hazard, and I'm getting in trouble for it, okay? Not you, me. So, you're sitting on the floor next week. That being said, the stream is up. One request, please don't be in the room and streaming it, because right now I'm going off Wi-Fi, so if you're streaming down while I'm streaming up, we're going to have a little All right, so our operating system of the day is called DTSS for the Dartmouth Time Sharing System, and this was released in 1964, and it ran on a GE machine, GE 200 series. And if you're thinking GE, don't they make toasters and light bulbs? Yes, they do make toasters and light bulbs, and once upon a time, GE also made mainframe computers. And for the record, so did your thermostat company, Honeywell. That's where the term honeypot comes from, actually. So this operating system is actually at Dartmouth College, and it was known for being the first operating system to truly put time sharing into use in general practice. This was the first one where they really demonstrated that preemptive concurrency, yeah, we can do that. And they wanted, when they created this operating system, they wanted as many people as possible to use it. They didn't just want to create some software tool like every PhD thesis where you write a 200-page document and the software and the documents sit on a dusty shelf somewhere. They actually wanted people to use it. And so they installed it at Dartmouth College, and they actually modified the curriculum of the school such that by 1968, 80% of the students at Dartmouth were using DTSS. Now you're probably thinking, oh, so it must have been a tech school. No. They had the geography students using it. The art students were using it. The history students, the math students, everybody was using it. And what's kind of funny is, there's always people who refuse to let go of history. This operating system remained in operation until 1999, which is probably when the professor retired. Now, aside from having preemption, it actually had a number of other features that were noteworthy. It had the first IDE. So you could actually write code and have it automatically inserted into the program and compiled and executed instead of having to do separate phases. But notably, the most important thing to know about DTSS is this was the first large-scale preemptive OS, which is really, really cool. And when they were doing this, by the way, you might be thinking, well, what was the scheduling quantum that they were using for this OS? Well, they wanted to make sure that no user had to wait more than 10 seconds for an operation to respond. Now, I realize by your standards, if you open VLC and it takes 10 seconds to respond, you're going to pick up your computer and you're going to toss it out the window. Oh, maybe you don't, but that's what I would do. If anything takes 10 seconds to respond today, that would be awful. But it is 1964. That's pretty damn good, especially for the time. All right, So in terms of announcements, I think you have a quiz this week. I'm pretty sure you do. And if you haven't already heard, quiz 2, everybody gets heard. I discovered after the quiz opened up that the questions were actually being changed, and I felt that this was not fair, so I decided everybody gets perfect on quiz 2. Free 0.5% of your mark, right? It doesn't add up too much, okay? The other thing I wanted to say is that, as I promised, I have made a Piazza post where I've started posting a bunch of extra lecture content. That includes guides for locks, condition variables. If you're struggling with context switches, it contains a whole bunch of content like that. It also contains the solution for lock that we had on the board in class yesterday, so that it's fair for not only people in this room, but for people in alley sections as well. Everybody gets everything. It's fair, right? So there's also right now a guide up there for condition variables, which is question 2 on your assignment. And at the end of today's lecture, my goal for you is to be able to go home, finish A1 in its entirety. There will be nothing else you will need after today to do A1. All right, so instead of going to slides right now, we're going to hop over to my web browser, or not my web browser, my terminal. And what I'd like to show you is actually the lock test. Because you're going to be, we just talked about how to implement a lock. And if you don't remember what a lock is, it's that thing we're using to make sure that we're the only person in the bathroom at once. It is a locking door mechanism, and we had spin locks where we wait by actively sitting there and knocking on the door. Hey, are you there? Are you there? Are you there? So spin locks spin, and locks block. When you can't acquire the lock, you go to sleep, which means you're not actively using CPU resources, and it's a little bit more efficient. So in order to test your lock implementation, there is the test SY2. And that is built into the kernel of OS 161. And if you have not read the Piazza post, I'm going to tell it to you now, do not run tests back to back in OS 161. It can't handle it. Because right now, the implementation of memory in OS 161 is when you say free, it says meh. Because the implementation is empty. Nothing is free right now. Nothing. There is no memory management in OS 161 right now. Until you implement assignment 3, you cannot run tests back to back. You must start the OS, run your test, shut it down, and go over again. So if you're trying to run SY2 back to back, and it's giving you some kind of bizarre error and kernel panic or freezing, yeah, you can't run them back to back. And it's not your fault, but you will fix it later, just not now. So I'd like to actually show you SY2. So this test can be found in kern test synchtest.c. And we're going to go to line 46. And I want to point out that we have 3 global shared values. We have test val 1, test val 2, and test val 3. These are the 3 shared values where all of the threads are going to be trying to read and write at the same time. So keep those in mind. And if you're wondering what this volatile business is, and you probably have noticed it through the slides, we're not going to talk about volatile today, but we will talk about what volatile is on Thursday. So just be patient there. So we've got these shared variables. And then on line 190, this is the body of SY2. This is our lock test. And what we're going to do is, for some number of iterations, we are going to do some computations with the value that is passed into the thread and store those computations in those 3 shared global values. So test val 1 will contain the thread number, test val 2 will contain the thread number squared, and test val 3 contains the thread number modulo 3. It's not exciting. And then after we have set those values, we are going to test to make sure that those values in the shared global variables have the values we expected them to have. We want to make sure that nothing has come in and changed those values while we own the lock here. And if any of them do not succeed, we will get a failure message, and that's it. All right. So this is the test. This is SY2. And let's actually run SY2 now. So I'm going to go over here to my other terminal, try to make the text a little bit bigger. And we are going to run the command. We're going to run the whole test from the command line. And I want to show you what happens if your locks don't work. So what happens if they don't work? So I'm going to run a version of my kernel that does not have locks. And if you can't remember how to do a test from the command lines, it is sys161, the kernel you want to run, and then in quotation marks, you're going to put the test, semicolon, Q, that's it. Just make sure there's only one test in there. So now we're going to run this. Oh my, what is all this garbage? That's called my locks don't work. Because, well, to be fair, I just ran it with something that doesn't have locks implemented at all. If the locks do not work, you will see some form of garbled output. Now, interestingly enough, this is one of those rare occasions where I ran it and I actually got the problem. But if we keep actually running this, we may run into a situation where it succeeds. And it looks like the locks work, even though I haven't implemented them. That may happen to you. It is not enough to run the test just once, or twice, or 3 times. What should you see then if the lock succeeds, or is correctly implemented? That's it. Lock test done, no garbled output. Now you might have noticed there was a small hesitation. This program ran a little bit slower than when I didn't have locks implemented at all. It's because, yes, when you start using things like blocking locks and semaphores and condition variables, it is going to have a bit of an impact on the performance because we are now synchronizing our threads and forcing them to run in a particular order, i.e. we're forcing mutual exclusion. And so we're not going to get the same level of performance out of things. But we have no race condition yet. So don't be surprised if when you run SY2, there's a few second delay. We expect that. We know that's going to happen. Now, how should you test your lock implementation? Step 1, run SY2. Don't run it once. Write a script that runs SY2 at a minimum of 100 times. Minimum of 100 times. If you want to do 1,000 times, you can do that too. And then go through, dump all of the output to another file, and sift through it to check to see if you get any garbled output. If you get any garbled output, then your locks don't work. If you are convinced that your locks work, you can also run the UW lock test. Verify they work there. And if you are at that point still convinced your lock works, there's one more thing you can do. If you want to increase the probability that you have a race condition, one of the ways that you can do that is to increase the number of CPUs. Now, we can actually do that in OS 161. If you look in the root directory, you'll see sys161.conf. So if we open sys161.conf, and if we go to the last line, you'll see main board RAM size CPUs. For now, modify the number of CPUs. Do not go higher than 16. I recommend testing on 2 and 4 because that's what we will be doing. We will be testing multi-CPUs. This is going to increase the probability you get a race condition if your locks are incorrectly implemented. So I'm just going to uncomment one of my existing lines here. And now I'm going to run it again. And what you're going to see when you have more CPUs, and this is totally normal, is you'll see each of those CPUs booting up, and you should see them shutting down as well. And that's totally normal. But if you run this 100 or 1,000 times, there should be no garbled output. I cannot give you a magical test to run to, with certainty, prove your locks work. I can't do that. What I can do is give you a technique for being statistically convinced your locks work, which is write a script and run it 100 to 1,000 times. Now, you might be tempted to go straight to running it on multiple CPUs, but the problem is if the race condition presents itself on multiple CPUs, it is much, much harder to debug it on multiple CPUs than a single CPU. So try to identify problems by testing first with one CPU, when and only when you are convinced it works on one CPU, then move to using multiple CPUs. All right. Any questions about it? All right. So that is all I want to talk about locks for now. So now, yes?
What would a loft test look like if you just implement the lock with a full lock?
What would it look like? So if I just, what would the lock test look like if I just made lock a wrapper for spin lock? I mean, it should succeed, but it might be really slow. And by the way, RTAs are watching to see if you're doing that. You are not allowed to just wrap a spin lock and call it a lock.
Then why one of the questions in quiz 2 is like when you have a spin lock or race condition is so comfortable?
We were asking you if that's true. Under a particular circumstance. If you want to talk more about the quiz results, we can do so after class, okay? All right. So, we have locks, and they're great. They're great for giving us mutual exclusion, so that we're the only person who can use the toilet, because there's only one toilet. But apparently at the Olympics, there were bathrooms where there were stalls that had multiple toilets in the same stall. Now you might be thinking, I've never seen that before, but I was a drill guy once upon a time, and all of our latrines, outhouses, they always had more than one suite. So what if I want, the point I'm trying to make is, what if I wanted more than one person to be able to come in to the critical section at a time? We could use the example of this room. There are 89 chairs in this room. And if you want to sit in this room, well, I can let not just one of you in, I can let 89 people into the room. And the 90th person and anyone beyond the 90th person, you're going to have to wait. What if I have some kind of multi-threaded environment where I'm counting the number of available resources? How do I do that with a lock? Can I do that with a lock? Actually, you can, but it's not what you think. We're not going to go over that right now. But as it turns out, there is another synchronization primitive we can use to count how many things are available and let threads into the section so long as there are still items available for it. And it is called a semaphore, and it's my absolute favorite synchronization primitive because they are so bloody versatile and easy to use. Now here's the idea behind a semaphore. When you want a resource, you're going to acquire a resource. And the semaphore, instead of having a Boolean, is now going to have a counter. And it counts how many resources are available. So when you acquire the semaphore, it's going to check, is there a resource for you? And if there is a resource for you, it will let you in, i.e. not put you to sleep. It will decrement the count of resources because you just took one. And if there are no resources available because the counter is 0, it puts you to sleep. That's what happens in acquire. And then on release, you are returning the resource. So we increment the counter, and we wake up any threads that may be waiting for those users to become available. That's a semaphore. And if we look at the implementation of a semaphore, it is almost identical to a lock. And in fact, if you are struggling with implementing your lock, here is the recommended path to implementing your lock in OS 161. Well, all of the function prototypes for locks are already there for you, so what you need to do is open up the implementation of Semaphore and copy and paste its code into the lock code. You're allowed to, by the way. And then make a teeny tiny change, and now you've got a lock. I'm not going to tell you what the change is. Hopefully you can resolve that from our previous class. You are allowed to do this. It is actually sort of recommended in the assignment specification that you look at the Semaphore's implementation. It's because it's almost identical. I didn't want to figure out how do I do all the initialization and stuff for locks, so I just copied and pasted it out of the Semaphore. It's okay, you can do it. Now, unfortunately, with semaphores, we don't call it acquire and release. They're called P and V. So the creator of semaphores, a gentleman by the name of Dykstra, he fails CS135 in terms of style marks because his functions, what the hell is a P? I'm P'ing the semaphore and I'm V'ing the semaphore, and believe me, I always mess which one is which. Because the names of the functions have nothing to do with what they actually do, or at least they don't in English. So my understanding is P, which is for acquire, is actually apparently this Dutch word. Or so I've read. I'm not going to try to pronounce these words. I don't speak this language. V, which is our release. Okay, I've got to look up the spelling of this one. Because I'm not going to spell it right even if I try. And there's no way I'm trying to pronounce it. That's apparently what the V is for. And apparently the names of these functions were inspired by train signals. But what you should know is that when you want to acquire a resource, you P the semaphore. When you want to release the resource, you V the semaphore. So I know it sounds very weird. You go around talking about P'ing and V'ing an object, but that's what you're doing. You're going to P and V the semaphore. Now, in a lot of other languages and a lot of other APIs, they've actually given the semaphore's P and V functions nice English names that are readable, good style. But OS 161 has decided to go with tradition and give you P and V. Make sure you remember which one is which, because this will behave very funny if you call them in the other order. All right, so as it turns out, there are lots of different kinds of semaphores. And what's interesting about this is they're not separate objects. There are just different ways that we can use the semaphore that give us different kinds of behavior. So for example, we can have something called a binary semaphore. And a binary semaphore is, if used correctly, it's like a lock. A binary semaphore is a semaphore that starts out with one resource. And you P and V it in such a way that before you enter the critical section, you always P, and before you leave the critical section, you V the semaphore. So the counter is either 0 or 1, which means it's effectively a lock. But it is on the programmer to make sure they use it correctly. There is no rules with the semaphore that says you can't V a semaphore 100 times. When you V a semaphore 100 times, you just increment the number of resources 100 times. So if you are using a binary semaphore as a mutex, be careful. Make sure you're not accidentally V'ing the semaphore too many times, because then you don't have a locking. The other thing with binary semaphore, and semaphores in general, is semaphores don't care about ownership. You can think about it this way. If somebody steals your laptop, that's your resource. What do you care more about? Do you care more that somebody returned the laptop, or do you care who returned the laptop? Now, I'm sure when they return your laptop, you might want to, do something about the fact that they stole it in the first place, but realistically, you're just happy you got it back. And the same is true for the semaphore. Semaphores don't keep track of ownership. So if you own a binary semaphore and somebody else tries to acquire it at the same time, or you try to acquire it again, there's no concept of ownership. So be careful about using them. So that's a binary semaphore. We're not going to see binary semaphores used a lot right now, but when we talk about devices much later in the course, you'll actually see binary semaphores have very good uses. Another kind of semaphore is a counting semaphore. That is a semaphore where we are using the counter to actually keep count of the number of items we actually have available. And what's interesting is when we're using a counting semaphore, you might be thinking that our semaphore must start with a fixed number of resources that is not zero. And actually, that's not the case at all. If I am a baker and I show up at the bakery at the beginning of the day, and I'm making cupcakes, my shelf has no cupcakes in it. So if people come by to buy cupcakes, I have no resources for them. But as the day goes on, I will bake cupcakes and I will increment the number of resources. Counting semaphores can start with 0 resources. You do not have to call P before you call V. You can call V first. The semaphore is just keeping track of how many resources are available right now. Then we have another fun use of a semaphore called the barrier semaphore. And you've seen it in my demo code that I show, but I kind of didn't even talk about it. A barrier semaphore can be used like thread join. So the idea is you want to force threads, a thread, to wait until all of the other threads have completed their task before you continue. This is used all throughout the traffic simulation, which is question 3 on assignment 1. And here's why we are using and how we are using a barrier semaphore. I am going to, in the traffic simulator, I am going to create a bunch of threads that are going to run the simulation. And each of those threads is going to run some number of vehicles through the intersection. Now me, the thread that forked off all these simulation threads, I want to collect statistics about each of the simulations that have run. But I need to wait until all of those simulations have completed before I collect the statistics. So I need a way to wait for all of those threads to complete. And I can use the semaphore to do that. So let's see the barrier then. So we'll go over here. And we're going to go into the sync probs directory. And this is the traffic.c file. And what you're going to see in here is there's this simulation wait semaphore. And its initial value is going to be set to 0. So there we go. On line 352, I create the simulation wait semaphore and I set its initial count to 0. And then what I am going to do is after I fork off each of the simulation threads, in a separate loop, I'm going to P the simulation wait semaphore once for each thread I forked. Now you will note I don't do it immediately after I fork, because if I did that, the threads would actually run serially. So after every thread has been forked, I will then P this barrier semaphore once for each of those threads. Since the initial count is 0, I'm going to wait until each of those threads V's that semaphore. And once every one of those threads I spawned off has V'd the semaphore, then I know they have all completed and I will move past this for loop here and I can collect the statistics and move on. So if we actually look at the code that V's it, it's right here on line 517. So this is the end of each simulation thread. What you're seeing there is us indicating to the barrier semaphore that this thread has completed. What I want to point out to you is that I just gave you 3 different uses for a semaphore, but I didn't actually change the implementation of the semaphore. It's the same implementation. It's just 3 different uses that give us 3 different behaviors. It's pretty cool. This is one of the reasons why I love semaphores so much, is you can use them to do pretty much anything. They're pretty sweet. Also, it is really funny to say you're being. Okay. So some examples of using some semaphores here. So you might remember when we started talking about synchronization, we had this silly little program where we were adding 1 n times and subtracting 1 n times. We used a lock to protect the critical section, where here I'm using a binary semaphore to protect the critical section. And because I always P before I V, and I never V more than once, it works out. But you have to be careful. It is on you to make sure you are using this correctly. So we start with our initial count, resource count set to 1. And we make sure that we never increase it beyond. Yeah?
Is there any difference between a semaphore and just a lock that asserts that when you, like, if I just wrapped it in something that asserts that it will P, like it will always be before being, is there a difference?
There is a difference between them because a semaphore doesn't keep track of ownership and a lock does. So locks can only be released by their owners. Semaphores, because they don't keep track of owners, anybody can be a semaphore. Anybody. We don't care who puts the cupcakes on the table. We only care that the cupcakes are there. That is it. Yes?
So in your traffic example, you had a global static variable.
Yes.
And then in C, if you have a static variable, you don't necessarily have to initialize it. So then how does what if it's not initialized and a thread tries to run functions on it?
If you actually look at the code for that, you'll see that it checks for null first.
Okay.
Yeah. So make sure when you're implementing, if you actually look at the semaphore's implementation, it's got a bunch of k asserts to make sure things like this is not null, and if you're using the spin lock, it also, actually I don't think the spin lock asserts if it's not null, but you need to make sure. Yeah.
Follow-up question.
Yeah.
If you have a static global variable, and then try to increment it or whatever, would that not be thread safe? Without logging it?
If you're trying to modify a global variable,
That's static.
but it's still global, which means multiple threads can still access it. So if you're trying to modify it at the same time, then you can have erase it. Yeah. Yes?
Other than efficiency, are there advantages to not keeping track of owners? Like what else would be?
Well, the thing about a semaphore is how many owners would there be? Because if we're keeping track of resources, what if our semaphore has 10,000 resources? Are you telling me that I need to keep track of 10,000 owners?
But that would be efficiency.
Yeah. I'm sure there would be some advantages if you wanted to ensure, if you had a situation where you want to ensure that the person who requests the resource is the person who returned it. So, to be specific, let's say you all rented something, we have to make sure that, and we want to make sure that you actually returned it, but our implementation doesn't do that. There's no reason for it. It's not really the use of this time. All right. So Now that we've got a few different synchronization primitives to work with, it's time to look at a concurrency problem. And as it turns out, there are many famous concurrency problems out there. There is producers and consumers, which we're going to look at. There's also the barbershop. There's the dining philosophers. There's a whole bunch. I know they all have cutesy names. Take 343, and you can learn all about them, and draw diagrams of a bunch of people sitting in a ring and trying to share chopsticks with each other. Yes, that's one of them. But we're just going to look at the synchronization problem known as producers and consumers. And here's the idea. Yeah, you have a question?
Yeah, so I have a question for the reason. So say if we have one thread to set a variable, and then there's several other threads to read this variable, but then we don't care if we read the number is before the set or after the set, but cannot be anything else. Then is that a reason?
So,
yeah, because I know some architecture, like first load the first half bit and then load the second half bit. If they cut in the middle, then it's neither the value before set nor the value after set. So I don't know if that's happening in OS.
yeah, OS 161 does not do CPU reordering. Well, sorry, MIPS 3000 doesn't reorder stuff. The compiler still can.
So it's still unsafe, right?
Pardon?
So in this case, it's still the code is still unsafe, right?
Yes. Yeah. All for us in our general implementation, you can assume that if multiple threads could be reading and writing, that there's a race condition. Don't make any assumptions about the architecture providing you with any atomicity. Don't make any assumptions about the compiler being intelligent. Neither of ours are that smart. Now, that's not to say that there are not architectures out there that can protect that and prevent that from happening. Ours can't. We'll talk more about the compiler and architecture's role Thursday. Okay. So for now, just race conditions, reading, writing at the same time. All right, so I do want to talk about producers and consumers. Here's what it is. So you have a finite buffer, and there are going to be two roles. There's going to be people that are putting things into the finite buffer, and there's going to be people who are taking things out of that buffer. The way I like to think about it is, let's suppose you are the Subaru plant down in Indianapolis, and they have a giant parking lot. Yes, I've been by there. And that parking lot is a finite buffer. They can only make a car if there's a place to put it. Because otherwise, if they just keep making cars and there's no place to put the cars in the buffer, i.e. the parking lot, then they're going to have to throw the cars in the garbage, which would be a waste. At the same time, the consumers are all of the little dealerships sending their transports to go pick up cars from the plant. And they're going to send these trucks from as far away as Nunavut to come get Subarus to sell. Do you send a truck from Nunavut to Indianapolis if there are no cars in the lot? You don't want to do that. That's a waste of time. So what we need is some way to synchronize this problem. I want to make sure that I, as the producer, do not produce any items if there's nowhere for me to put them. Don't make cars if you haven't actually sold any. And at the same time, if you're the consumer, don't go get some from the lot if there are no cars available. So we want to synchronize this little problem. And as it turns out, you can do this with semaphores. So take a couple minutes, see if you can think about how many semaphores you need to solve this problem. What those semaphores' initial values should be. And if you're having a hard time thinking about this particular problem, the first thing you need to think about is what is the resource for the producer and what is the resource for the consumer. So take a couple minutes, talk amongst yourselves, and we'll see if anyone catches it. of you looked in your notes? The answer's on the next page. Well, sort of. So as it turns out, to synchronize the producer's consumer's behavior, you need two semaphores to do that. You need one semaphore for the producer. It is keeping track of the number of free spaces there are. When you start the system out, there are n free spaces. And to the consumer, its resources is the number of items in the car lot. And at the beginning of the day, there are none. So one semaphore to keep track of spaces, one semaphore to keep track of items. And then what we're going to do is the producer wants a space, so it P's spaces. Once it gets a space, it can add an item to the buffer, and then it doesn't V spaces, it V's items. Because it took a space and produced an item. And similarly, the consumer wants an item, so it P's items, and when it takes an item from the buffer, it is making a space, so it V's spaces. However, the reason why the correct answer is 3, not 2, as this slide would have you believe, is because we're simply managing whether there are items for people to take or spaces to fill. We have not actually protected the buffer itself. So it is entirely possible that if there's spaces and items in the buffer, that a producer and a consumer is trying to add and remove from the buffer at the same time. So this solution that's in the slides is not actually providing any synchronization for the buffer itself, i.e. mutual exclusion. Now you can add a lock to protect the buffer, or you can use a binary semaphore. That's out of same thing. Alright, any questions about producers and consumers? Yes?
So let's say if we know that there are 1,000 carbon spaces and both consumer and producer know that number, we only need, let's say, the amount of space that we have, because you can subtract it from the buffer and say these many parts are there.
Ah, so you just want to access the count variable inside the semaphore. You can't do that. That's not safe.
I mean, there could be a good variable, which is like, it says that these many parking spaces are there.
And then we only need lock to do it, really. So you actually pointed out an interesting problem. So number one, with semaphores, the count is supposed to be hidden. The user, whoever is using the semaphore, should not be accessing the count inside the semaphore directly, because that would not be safe. Number two, what you're going to see today and tomorrow is that most of these synchronization problems, there's more than one solution. We've given you a solution with semaphores. You could do this with locks, and you can do this with what we're about to introduce in condition variables. There is more than one way to do it.
Also similar to that, doesn't it not matter whether or not you have this, because all you care about is whether or not there are items / there are spaces. So you just need to use the fact that you have a greater than, or like if you were to do like the one semaphore that was tracking empty spaces, you would just care if there was greater than 0 empty spaces.
But that's the thing with semaphores. We don't look at the count.
But you don't need to tell me, like, doesn't
P and V,
check it, if you check it.
P, if the count is not 0, decrements the count. And if it is 0, puts you to sleep. So it doesn't return, yes, there's an item, or no, there is no item. It doesn't return a count of how many things are available. We do not have access. If this was implemented in C++, the count would be private. And there's no functions to access the count. So when we P and we V the semaphore, we don't actually know what the value of the count is.
Wouldn't it like you go to sleep instead of actually on the buffer?
But if you're asleep, how do you know? Because you're sleeping, you're not executing code. All right. So what I'd like to do then, one more question.
Why don't you give access to that?
If you wanted to have access to the semaphore's counter, you would have to do it with mutual exclusion. Because if you are somebody who's trying to P or V the semaphore at the same time you are checking the count of the semaphore, there is a chance for a race condition. We do not, in our implementation of a semaphore, have atomic access to count. It's dangerous. I'm not saying there aren't implementations in semaphore that do that. It's just generally speaking, with semaphores, we P and we V, and that's it. All right. So let's look at the implementation of the semaphore. And this is out of the code that is given in OS 161. Hey, wait a minute. Doesn't that look like a lock? That looks almost identical to the lock code we showed the other day. There's a reason why I told you to copy and paste it into the lock. Yes, I know I built the KS certs out. You can add them back. All right. So what you can see here is the semaphore's implementation is nearly identical to the lock. Couple small differences. Number one, instead of a held, we have a counter. Number two, there's no ownership. And that's about it. There's not much of a difference between them. And one of the things you'll note is when the count is 0, that means there are no resources available, and so we need to go to sleep. And you'll note, again, we lock the wait channel before we release the spin lock, and then we go to sleep. So let's actually walk through a bit of code that is going to show you why it has to happen in that order. And by the way, I have this for a lock already posted to you guys. So let's suppose then we have incorrect semaphore implementation where we lock the wait channel after we release the spin lock. So I'm going to release the spin lock and then bam! Out of our control, we get a context switch here. Remember that context switches can happen anywhere at any time. It's out of our control. So I'm arbitrarily saying, let's suppose the context switch happens here, because it could. So it happens there, and now we switch to thread 2. And let's suppose, by the way, the semaphore initially has no resources. Now, my thread 2 is going to be the semaphore to produce the resource. So it increments the count, and then it calls wait 1. Okay? So at this point, you should all agree the semaphore has a resource that is available. Finishes, returns, context switch back to thread 1. And what does thread 1 do? Oh, it locks the wait channel and it goes to sleep. Which means that this thread just went to sleep on a semaphore that has an available resource. That is, if you put those two functions in the wrong order, that's what will happen. So now, what should happen? All right. So let's suppose we lock the wait channel before we release the spin lock. So we lock our wait channel, and we call spin lock release, and then there's our magical context switch that's going to happen. Now, does it mean it always happens here? No. I'm just saying, if it happens here, which it could, what happens next? So our thread 2 calls V to produce the resource. It calls spin lock inquire, it increments the count, and then it calls wait 1. But inside of wait 1, the first thing it tries to do is acquire the lock on the wait channel. And wait a minute, thread 1 owns the lock on that wait channel, which means that thread 2 falls asleep inside of wait 1, and there is a context switch inside of wait 1 back to thread 1, where thread 1, since it owns the lock on the wait channel, it can go to sleep. Inside of sleep, it will release the lock on the wait channel once it is on the queue, and then it will have a context switch. We will go back to the other thread. The other thread will wake up inside of wait 1. It will succeed in acquiring the wait channel lock. It will then wake you up, move you from blocked to ready, and then it releases the spin lock. When you run again, the resource is available, and you now have a chance to acquire. It is very important you put those two functions in the right order. All right. So we've got half an hour left in class. If you want me to go over this again, by all means, please stop by office hours, which are right after this class. I'll take one question from up here then. Blue shirt.
So a context switch can happen with a custom lock applied because like the one's locked or
So when we have spin locks, when we own a spin lock, interrupts are disabled, which means preemption can't happen. But there are 3 other reasons a context switch can occur. Thread exit, thread yield, and thread lock. So just because we have a spin lock doesn't mean we can't have a context switch. Just keep that in mind.
and in this case what would be the reason would it be yield or that cause the context switch?
Yes, it wouldn't be yield in that sense, but yield would get called.
Okay.
Yeah. One more.
Just a quick confirmation. The reason that we can't have WHN lock with WHN C is because of this component switch.
That's exactly it. Yeah. All right. So I'm going to conclude our discussion of semaphores there. If you have more questions about how they're implemented, why things need to go in that particular order, I have outlined that trace for a lock as well. It's the same reason in a lock as it is the semaphore. But I would like to move on to the last synchronization primitive we're going to do, in particular because this is, part of assignment 1. And that is this magical thing called a condition variable. And, at a high level, what a condition variable is what happens if you're inside of a critical section, protected by a lock, and the lock specifically is to protect access to some shared variable x. But inside that critical section, you realize x does not have the value you want. You really need x to be 5, but x is not 5. But you own the lock, so nobody else can modify x. So you're kind of at this, you're stuck. You can't make any progress because x is not 5, and nobody else can modify x because you own the lock for x. What a condition variable lets us do is safely fall asleep inside of the critical section while releasing the lock so that the condition can change so that we can, in the end, make progress. I have another way of thinking about this. So, suppose you go to a bar because you're lonely or you really like beer. I don't know. You go to a bar and maybe you get a mug of beer. I don't drink beer. You've got a beer in your hand. All right, mug. While you are holding on to the beer, the mug is going to be the shared resource. You own the lock on the mug. Only you can use it. So you have the lock on the mug. You lift it up to take a drink and you're like, I'm out. But the bartender can't fill your mug up because you have the lock on it. You're holding on to it. And they're not going to try to refill your mug while you're sitting there shakily holding it like, eh. So what we need is some way to simultaneously put the beer down and fall asleep. That's what we need. And then the bartender will be like, oh, okay, now it's safe for me to refill it. So they pick up your beer mug, they fill it back up, and then what they're going to do is simultaneously release, smacking you on the head and waking you back up. And as you wake back up, you grab your beer and you're like, oh yeah, sweet. I got beer now. That's what a condition variable is going to let us do. It lets us fall asleep inside of a critical section, such that the moment we fall asleep, we own the lock, and the moment we wake up, we will also own the lock. That's what we are doing. We are giving the ability to some other thread to modify the condition so that we can proceed, and to do so safely. Now, a condition variable has 3 functions. It has wait. Wait is what is going to put us to sleep, release the lock, wake us back up. Well, we will wake up back inside of wait, and then we reacquire the lock as we leave wait. An important note about wait. When we are inside of wait, when we call wait, we own the lock. When we return from wait, we own the lock. That is a key feature of CP wait. Then to wake up a thread, we have signal, which will wake one thread, and we have broadcast, which wakes everybody. All right. Well, how do we use these things? Well, if we look at that producers and consumers problem, we were thinking about it with Semaphore in terms of resources and availability of those resources. Condition variables, we're looking at what is the condition now. The condition for the producer is the count of items in the buffer has to be less than n, the capacity of the buffer. Because if the count is less than n, then there is space. And if we are the consumer, we are waiting for the count to be greater than 0. Because if there's more than 0, then there's items in the buffer. Those are the conditions. You have one condition variable for each condition. Now you might be wondering, do I have to pass this condition as some kind of like function pointer to my CD? No. No, you're going to be managing that side of it. You check the condition, and if you do not meet the condition, you will call CB wait to put the thread asleep. And then when you change the condition, when you change that value, you call signal or broadcast to wake up the other threads. So it's on you to actually maintain the condition itself. All right. So let's kind of look at how we get this behavior. So we're going to have this little piece of sample code here. You know, there's lots of geese on campus, and maybe you're terrified of geese. And so it is only safe to walk if the number of geese on your path is 0. So while the number is greater than 0, you have to wait. So we have this function called safe to walk, and it's going to return 1 if it is safe to walk, and 0 if it's not. So, well, the number of geese is a shared global value. And so I need a lock to protect my access to it. So I have this geese mutex. And so in order to check the number of geese that are there, I'm going to acquire the lock. Now why do I need a lock on this? Well, I'm checking the number of geese, and the geese might actually be coming onto campus and leaving campus, right? So they may be changing that value. So we need a mutex around it. So I acquire the lock, and then I check. Is the number of geese greater than 0? Well, starts at 100, yes. Yes, it is. So how am I going to go to sleep here? How am I going to wait for this condition to be true? Okay, well, here's one way we can do it. I could say, instead of if the number of geese is greater than 0, say, while the number of geese is greater than 0, I release my hold on the lock, and then I immediately reacquire it again and check the condition again. Essentially what I'm doing here is I'm continuously checking the condition, and in between each check, I release and reacquire the lock. Now maybe that doesn't make sense to you, but let me tell you why we're releasing and reacquiring the lock in the loop. When I release the lock, I am giving the opportunity to another thread to acquire that lock and change the value. Yes?
Why don't you thread yield after the release?
You could do that actually, so which would give you a greater chance of actually giving the lock to somebody else. But you don't have to. This will succeed by you. All right. So this is one way you could do it. Yeah, I'm effectively spinning here. I don't really like this. So what else could we do? Well, this is what we would do if we had a condition variable. If we had a condition variable, we are going to take away the lock release, lock acquire, and we're just going to call CV wait instead. That's what we're going to do. Now what happens inside of CV wait? So I will give you a rough idea as to what happens inside of CV wait. Put it here on the board. So CVs have to be used with a lock. And remember I said that when we enter CV wait, we must own the lock. And when we leave CV wait, we must also own the lock. But I want to go to sleep. So I want to, inside of CV wait, I want to simultaneously, and I apologize in advance for my spelling, I want to release lock and sleep. And then when I wake up, I want to reacquire the lock. Okay. Now, what lock? The lock that you pass into CV wait should be the lock that you are using to protect that shared variable. Should be. And what you can do is you can release the lock. And then you're going to go to sleep. Two things. We have to lock the wait channel, don't we? Where do we do that? At the back there in the center? Before you release the lock, you need to lock your wait channel. Now wait a minute, what wait channel? Whose wait channel am I falling asleep on? Any thoughts? How many of you say I'm going to fall asleep on the lock's wait channel? How many of you say I'm going to fall asleep on the CV's very own wait channel? How many of you are totally lost? That's okay. The answer, not just by majority vote, the correct answer is the condition variable has to have its own wait channel. We are not waiting on the lock, we own the lock. We're waiting on the condition. Each wait channel is for one and only one thing. I shouldn't be waiting for a lock and waiting for a condition on the same wait channel. That doesn't make any sense. So your condition variable needs to have its own wait channel, and that is what we fall asleep on. Then, of course, we reacquire the lock and we leave. Now, there are some pieces missing from the pseudocode for a condition variable that I have not given you. There are some assertions we should be making, for example. Like, if I pass in a lock that's null, that's going to be a problem. If I pass in a lock that I don't own, that's going to be a problem. And make sure that when you're checking the ownership of a lock, you're doing so with the lock do I own function. Don't just code it directly. Use lock do I own, it exists for a reason. That's CV wait. Now, are there spin locks inside of a condition variable? No. There's no spin lock needed. We don't need a spin lock because we are past a lock itself. We will use that lock that we are past. We don't need anything else. If you want to know how many lines should your condition variables take, not very many. They took me 2 minutes to implement because there's not much code to them. It's significantly less code than implementing a lock. Very, very small. Now what about signal and broadcast? Well, signal is going to wait one thread up. Wait one. Broadcast, we wake everybody up. Wake all. That's it. Now, a lot of you are going to ask the question, why does CB signal and CB broadcast take the lock? We don't use it. Right. For our particular kind of condition variables, we don't need the lock parameter inside of signal and broadcast. You're absolutely right. We don't need it. The kind of condition variables that we're using is called MESA style. There are other kinds of condition variables out there. In particular, there's another condition variable style called where style, and they behave very differently. When you signal a where style condition variable, what's going to happen is the thread that is woken up is going to immediately run, and the thread that did the signaling is actually going to fall asleep. It is a little bit trickier to implement, but the reason why they exist is because when the condition changes, where style is more responsive to handling that change in conditions. So you don't typically see where style CVs implemented for plain old operating systems, but for a real-time operating system, it actually makes a lot more sense. Now, there's another interesting fact about condition variables. When you wake up, when somebody signals you, you wake up inside of the wait function, right here. So you've just woken up. When you wake up, you get pushed into the ready queue. You don't run, you go to the ready queue. And then we have to wait for you to be scheduled to run. And then when you run, the next thing you try to do is acquire the lock so that you can return to the critical section. But what if somebody owns that lock? Then you go back to sleep again. So you woke up only to go back to sleep again. That doesn't really make a lot of sense, does it? So there's this concept called weight morphing, which can be implemented with a condition variable, and the idea is that we can actually take you off of the wait channel of the CB, and what if I just put you directly onto the wait channel of the lock? What if I morph, instead of causing you to go from ready, running, back asleep, back to ready, what if I just noticed that the lock was not available and just directly put you right on in that lock's wait channel? Bypass this whole wake up and fall back asleep. So that is one improvement to the performance of condition variables we can do. It's called weight morphing. It's not in your notes. All right. Now, we don't require that you implement them that way. You can implement plain old MESA style condition variables. You don't need to do weight morphing. I mean, I'm not going to stop you, but. Okay.
So in our style of locks, after we wake up, or sorry, not locks, condition variables, after we wake up, we don't let go of our lock, we keep holding on to it till we're done. So like if another thread calls the signal to wake up, it still continues to own the lock.
Yes, that is how you should use them. Let me explain the reason why. So the thread that is doing the signaling is the thread that presumably made the condition true, right? And we need to own the lock in order to make the condition true because that was modifying a global shared variable or a heap variable. So when we signal, we want to make sure that it is guaranteed at the point of signaling that the condition is true. And the only way that we can guarantee that is if we own the lock when we call signal. Which is why when we call signal, we own the lock. And then usually after we signal and we return from signal, we would then release the lock. It's not an explicit requirement though. We don't keep track of which lock is used with the CB. We just care whether we own the lock that is passed in. We don't do any tracking. Now what's interesting is because of this, it's entirely possible that even if I own the lock when I signal, it's entirely possible that the thread I just woke up, when they actually wake up, the condition has changed again. because we don't have control over when that thread is going to run. And it's possible that another thread stole the condition out from underneath us before we got to go. Which is why, when we are using condition variables, we will almost always see them used with a while loop. So that when we wake up, we are rechecking the condition before we proceed. Now, it is possible with a condition variable to not have the while loop. But if you're going to do it in such a way that you don't use the while loop when you wake up, you have to do an explicit handoff. So you have to make it so that when the thread wakes up, it is not possible for any other thread to steal the condition out from under you. And we will have an example next class of that. And I can tell you that the optimal solution for the traffic problem does that too. But I'm not going to. I will give you hints for the traffic problem on Thursday. Give you a few days to think about it. All right. So, what I'd like to show you now is, I'll turn these spotlights off here. I'd like to show you now how to implement producers and consumers with our condition variables. Now remember that with condition variables, we also need a log. So in this case, I have a count, which is to keep track of the number of items in the buffer. And then I have a lock, which I am using to protect the count. And I have two condition variables because there are two conditions. One is I'm waiting for the buffer to be not full. And the other is I'm waiting for the buffer to be not empty. So I have one CV for each of those conditions. In the producer then, because I need to test and check the actual count, I acquire the lock, and then I'm going to check my condition. I cannot produce an item while the count is equal to n, because that means the buffer is full. So while the buffer is full, I call CV wait, and I am going to wait on not full, because I want the buffer to have some free space in it. So I fall asleep on not full. When the buffer is not full and I wake up, keep in mind that when I enter CV wait and when I leave CV wait, I own that lock. So this is safe. So I check the count, there's now free space. Now I am free to add my item to the buffer. I increment the counter to indicate I've added something to the buffer. But I've just changed the condition of not empty. And so after I've incremented the counter in producer, I am then going to signal not empty. To say, hey, I produced an item. So you might be actually able to go now. So I signal not empty, and then I release my lock. Now why did I signal instead of broadcast? Well, I only made one item, which means at best one thread can get that one item. So it doesn't make sense to wake everybody up only to have 999,000 of them fall right back to sleep again. So only wake one if only one can proceed. All right, so that is the producer's code. Yes?
Could you improve the performance by wrapping the CV signal and lock release at the very bottom in like a spin lock, so that like acquiring a spin lock, because if you do that, then you won't get preempted before you release the new text, or is that not really useful at all?
No, that wouldn't be useful. The only way that you could really improve the performance here is to do weight morphing. Yeah, where you're just going to take, you notice the fact that the lock is acquired, and so you would just move the thread you are waking from your wait channel directly to the wait channel of the lock, such that when you release, you're saving a little bit of time.
Could you release an end signal while the signal is being released without?
Technically, in this implementation, you can, because we are checking the condition in a loop. So it doesn't matter. And actually, I have a rather long guide that explains exactly the reasons for this, and it's posted to Piazza as well. It's just extra content. All right, so that's the producer, and here is the consumer. It looks almost the same, but now we're flipping the conditions and flipping the CVs. So we have, in consume, we want to take an item, so I need to make sure that the count is bigger than 0. So while the count is equal to 0, I am going to call CV wait on. I'm waiting for it not to be empty, so I call CV wait on not empty. Once I wake up and indeed count is greater than 0, then what I'm going to do is I'm going to decrement the count to take the item, but I just changed the condition for the producer, so I have to signal it by calling signal on not full because the buffer is now not full, and then I release my lock and I can return the item. It is a little bit more code than using semaphores. Okay. Now, I'm going to save most of my traffic simulation hints for Thursday because I do want you to have some time to think about this on your own. You have everything you need to implement CVs. They really are really short. But I do want to give you one major bit of advice for the traffic simulation problem, which if you haven't seen it yet, you have a four-way intersection. And right now, it's implemented such that only one car can go through the intersection at a time, which obviously, that means it takes you 6 hours to get from Icon to here. So, what we want you to do is improve the throughput through the intersection while ensuring there are no accidents. You can use locks, you can use condition variables, and you can use semaphores. And I'm going to give you the advice of using locks and condition variables. And I am also going to give you a piece of advice. The wrong number of condition variables is 1. The wrong number of condition variables is 8 or 12 or 16. It is not that you can't make it work with that number of condition variables. It's simply that you won't be able to make it within our timing constraints if you have that many or that few. There is a correct number to use. Here's my hint. Think of, the navigational rows. It's not that semaphores can't be made to work, but I can tell you in the few years that I've been teaching this course, I don't think I've ever seen anybody get it working in the correct timing. You're welcome to try, but I would go with the one lock and some number of condition variables. That's your best bet. And I will give you more hints next class.
Yeah.